Okay, sorry about that. Yeah. Yeah. So it shows it's recording. So this is the first problem wherein we actually need to go through a list of words and compare it with a pattern, and then we return the list of the words which match a pattern. Okay. So you guys can actually see my notepad now.
Yeah.
Okay. So the first prob example actually is given as a list of words. These are the list of words, and then this is a pattern. Okay. So we need to match these list of words, and the way it has to be done, it says like every letter in a pattern has to map with another letter in a word, and no two letters should map to the same letter. Means no two letters of a pattern, okay, should map. Okay, no two letters map to the same letter of a word. And also, to just take an example here, if I say this is a word like a DEQ, okay, and then we have a pattern ABB, and if I map the first letter D of a word with the pattern letter A here like this, okay, and then if I map E with B, so this way, and then I go and map another letter of the word as a Q with B. So this is the mapping. But when I actually go for mapping from a pattern to the word, like I need to actually validate whether the mapping is correct. If I map from letter in the pattern as A to D, and then I map from B to E, and then I come to the last one where I try to map it with another uh, B with another letter which is different than the one which was previously. It means it's contradicting the problem statement, and therefore this word won't be a part of our answer. And similarly, like if we have a pattern which has very uh, distinct letters, and they are not mapped with the distinct letters in the word, then that word also won't be a part of this pattern. Okay. And actually this is the pattern where every letter in a pattern maps with every letter in the word, and therefore this is a part of the answer. Okay. So I think this problem statement is clear, right? So do you have any questions on that?
So let's suppose I have the word is ABB and the pattern is CCD. Would that match? But not.
Word is ABB.
Yeah.
And pattern is
let's say CCD.
CCD. Okay. So in this case, like if I map the first letter of the word with something like a C, right? And then I go map the other letter of the word, the second letter of the word B, which is B, to C, right? And then I come and when I start mapping this B with the D, but actually it is not fulfilling the requirement because I've already mapped B with something else, right? So I cannot map same letter with another letter. So therefore, this won't be a part of the answer.
But in this case, we map both A to C and B to C. That's
And
not allowed, right?
the order matters. Sorry, come again. I did not get the way you said.
In this case, we map A to C,
Right.
and B also to C. That's not allowed, right?
Okay, so this is not allowed. That is fine. Okay, but this is also not allowed. So the way I'm saying is, okay, so the implementation way is like we need to have two different maps, okay, So that is what the solution also states. Like, okay, the first part of the solution says like you need to have two different maps, which is one will be a forward map and second will be a reverse map, right? So the forward map will map all the letters from a word to a pattern, and the reverse map will map all the letters of a pattern to a word, right? So either of which we need to find the contradictory condition. And wherever it contradicted, we said we are not going to include that in the answer, right? So we need to check both ways. So this is also not correct, right? So when you are mapping A to C, and then when you are mapping B to C, and again you have another B which you are mapping to D, so that is also not going to work. Either way, like if you see C is mapping to A from pattern to word, if you go this way also, like if I map C to A, right, and then we try to map another C, but this contradicts here. You got it, or is it not still clear?
Yes, I got it.
Okay, sir.
And the word the length of the word and length of the pattern should be same here.
Yes, exactly. Yeah, sorry about that. I didn't mention it earlier. It has to be same.
Okay, got it.
Yeah, and also in this implementation, when I'm going through lead code, it doesn't talk anything about lower cases letters, But when I tried everything, it is only using lowercase letters. So that is what is not very clearly mentioned in the problem statement. But for now, I'm assuming we are going to be given only all letters will be lowercase. So that is what I'm trying to assume now. Okay. So the implementation, as I said, will be as well as it's explained in the solution. There are two implementations what they state. One is using maps, two maps, and other is using a single map. And there might be several other ways to implement also. So in the map, there will be two maps. One will be a forward map and other will be a reverse map. So the forward map will be like this one. If it is forward map, it is mapping all the letters from a word to the letters in a pattern. And there will be another reverse map, which will be mapping from all the letters from a pattern to all the letters in the word. And wherever there is a contradiction, we actually just don't include that word in our list. And the other way, just doing a single map will be like use a map as a forward map and then use an array of a length 26 and then check whether there is any duplicate in the values. So the reverse map actually what it does is if I use it for implementation as a map, I can include a key, and then if I include a value, I can overwrite a value, right? But yeah, I prevent in this case, but the reverse map actually does the exact reverse way of it, because here in the forward map we include all these word letters as a key, and in the reverse map we include all the letters of the pattern as a keys. So therefore whenever we try to re-enter the similar key, we can catch it there. So instead of using a second map, I can use another array, and I just look at the values of the first map and then find if there are duplicates. If there are duplicates, it means this pattern, this word is not matching the pattern, and don't include that word in the answer list.
Could you give an example? Like, using the first is a map, the second is an array.
Okay, so this, if I take this example, okay, if we don't have this one, and we are having like we are mapping this word. Okay, so if we have something like this, Okay. So we have a word DEQ and a pattern ABB, and the forward map we are mapping is the first letter D with A, and then the second letter E mapping with D, and then the third letter Q mapping with B. Okay. So then if I have an array, okay, maybe I call it something like okay, repo or something like that, then I have a 26 character array. Okay. And if it is an integer, I actually go, so I have all these 26 characters, something like that. So first I go and traverse each and the whole map and pick up the value. I'll pick up the value of A first and then map it over here. So if, okay, if this is a, okay, array of like bull, okay, and they're all initialized to false values first. So I mark this location as true because this is A, okay. And then I come here, go for the second element of the map, and I take its value, which is B, and the second location also will be true. So then when I come for the third one, okay, I come to this location and find this value is already true. It means there is a contradiction in our condition, and therefore we don't include it. So we need to only set this value, change this value to true only if it earlier is false value. Okay.
It seemed to me that we not take the order in consideration, because let me see.
Because what happens, the order will automatically come when we are actually mapping it, right? So first, when we are mapping it here, therefore we use one map. So we actually have an order already set, right? So even if the order, even if we take an example differently, like, if we have something word, which is some, maybe your previous way, like, you said something CCD, right? And the pattern is something like this. Okay, ABB, right? So this map will be like you mapping C. Okay, so anyway, this is not going to work because we already have a contradiction here, right? So this won't work in the map itself. Okay, so for this example, actually, to verify the array condition, this is the correct example because we want to verify the reverse mapping, right? So for
Can
this
you do
mapping,
the, sorry, can you use the word DEE?
word DE,
Yes.
okay, and the pattern
Pattern is same.
same. Okay, so in this case, what will happen, we will have letter E, D map to A, and then we will have E map to B, right? So that's the only two conditions will have map, right? Because the second, when we come to map E to B, it's already there. We don't have to map it. Okay. So now when we actually run through this map, okay, so we have A here, okay, and then we set B also to true. So we don't have any other element in it because we don't want to have duplicates in the map, right?
Okay, yeah, thank you. Like we will create the array with the map value.
Exactly, yeah. So we are only just going to look at the map values because that is the way we are actually verifying in the reverse map also. So we are just using an array here. Just a small optimization. I don't think it's a very big optimization. Okay. But the other way it could be implemented, instead of using all these things, we can have something like a normalized way, So instead of using all the arrays, all the maps, we can use something like what we say, a vector. And so if we have a pattern like this, right? If we have a pattern, say something like first A, B, B. And then we can have a vector which starts with count, like first for the first word, first letter, whatever we find, we set it as 1. And then we find another letter, we set it to 2. And then we come for the second one, we use the same because it's already there. So use the same value. But in case if we have some a pattern like a slightly bigger one, okay. So in this case, what will happen is the C will be value 3 and D will be 4, 4, and B already is there. So I'll mark it 2, 2, and then E will be 5, right? So then if I have a word to match with the pattern, something like MEEK and then NNEEF, okay. So if I normalize this word also to similar with the pattern, so 1, then actually I can have this, because I start with first count and then I start to go to the, when there is a transition in the word, I mark that as a 2, and this E is not already there. So, but now the E is already there. So I use the same count here. But when I come to K, which is not already present, then I make that as a 3. And so similarly for N also, but here N is there, so I mark that as 4. And then E is already there, so its value is the same, like 2, then another 2, and then we'll have 5. So if we say, if I compare these two values, okay, so it means the pattern and the word are matching. So instead of having maps, I can use this way, like having an array of integers. First create this pattern array, and then keep on looking for each and every word, a letter of the word, and then compare that with these values. So this implementation is also slightly better than using maps.
This implementation, I think we don't need to repeat the number, right? I was thinking. So, you know, if we see that 2 can be only 2. So let me see, A is would be 1, and if we see 2B and we put 2 in there, and then C is 1, we put 1.
Oh yeah, that might be a different way of doing it, you know.
And yeah, if that works, then we don't need an array. You only need an integer.
I didn't try that way, but I tried this way. It works. And so are you saying, like, you know, in A, so you're saying like if it is A, I make it 1, okay?
Yeah.
And then
we have 2B, so we put 2.
Oh, so you're just counting the numbers?
Yeah.
Oh, but in that case, then it might not match, right? If we have something like this, M, K, N, E, E. So how are you going to verify that? Because the order is different, right?
No, in that case, M, K, your M is 1, K is 1, N is 1, so be 1, 1, 1, and then 2. We have 2E, right?
Okay, so you are saying like if it is 2, just
I just count the number of same character. Yeah.
Okay, so then you want to go through each and every time and look at, okay, there are two of these. But what happens if we have something like this? You know, you have 2 B's over here and these 2 B's over here, so they have to match. So that's what the pattern says. So in your case, if you say 1, 2, then you make for C 1, and again
right?
for 2,
D is 2,
and again 2 and 1, right? So in that case,
Yeah.
you won't be able to differentiate between BB and DD and then BB, right?
Yeah, but if let's say if you have another word that will match, because we follow the same pattern.
No, actually we need to actually look at this BB also. See, like the BB should be here. Like in this case also we have EE here, so we have to have EE. So these things should be mapped. You know, if they don't map, then that's not a pattern.
Yeah, right. Yeah.
Okay. So,
but we can keep a map like you did.
Yeah.
Count it,
Absolutely.
right?
Yeah. So I said like there are various ways of doing it. So the solution itself is of two maps and a single map also. That's what I explained earlier. So I thought the other way to implement this is using an array of words as a template and then keep on comparing it. So that also gives an efficient time complexity. So I thought just it's worth sharing it, that's all. Okay, so the map actually is very easy. I'll just quickly run through the implementation. Okay, so this is the function entry point wherein actually you run through each and every word. And this is the function actually compares each word with a pattern. And if it is present in that pattern, word is present
Hey,
as per
Santosh.
the pattern. Yeah, sorry, word.
Like I'm not able to see your screen. Are
Oh,
others able
so
to?
sorry. I'm sorry. Okay. Yeah. So is this visible? Yeah. So, this is the entry function. And then I'm actually going through the list of all these words here. And then I actually compare all this with the function match. And if it is present in the match, then only I add to the answer list. So this function is implemented this way. Okay, it is a two map solution. I've set two unordered maps, character to character mapping, and then I run through a word. Okay, because the word length and the pattern length have to be the same. So I'm just using the word size over here, and I'm taking first letter of a word and first letter of a pattern, and then I'm just verifying if that is already there. If it is not there, then I map the word character with the pattern character here. And similarly, I do it for in the reverse map with the pattern character and the word character. And immediately I try to compare if those map, whatever values, what I've just inserted are the same. If they are not, it means it's a contradiction.
Yes.
Okay. So this is a two map method. And the single map, what I was discussing was like this. So first the map actually is already using one map, it's already mapped with the pattern the same way. But then if we find a contradiction here with the maps, then we return as a false, or else we actually run through the list of the values of that map, and then we compare if any of them is already present in this visit array, so we return false, or else we just return true. Okay, so this was a single map implementation. And the one what I was discussing with the templates was something like this. First, I actually normalized by using an array of 26 and then create a template. So just run through each and every letter in a pattern and then check if it's there in the frequency. So if it's not there in the frequency, actually I add that to a frequency and I start a counter value here, which is 1, which is initialized to 1. So I mark that as a 1 over here. And also I have a template vector wherein I store these counters. So for the first A, as I showed in the earlier one, will be 1 and then increment the count. So whenever I see the same alphabet coming back, I pick up from that frequency array and then assign it to the template array. Okay, so once I'm done with the template, I go for each and every word and do a similar comparison over here for each and every word. And if I don't find them, then I just break and don't include them. Okay. Do you have any questions on that? Okay, so there is nothing, so I'll just, so shall I move to the next problem?
Do we talk about the runtime complexity and space complexity?
Okay, so the runtime complexity, what I think is, because I run through each and every word, okay, and also I run through pattern, comparing the pattern with each and every word. So it is linear, but also it includes the pattern for each and every word. So maybe words, O of words into pattern, something like that.
I mean, like maybe length of the word.
Yeah, the length of word plus the word list, right? So length of the word plus, yeah, and then you have a pattern also. So pattern is being compared every time.
The time, right? The length of the word time the n, where n is the size of word in the list.
Yeah, so the words and the length of each word. So if we compare that as a n, and then we have all the patterns also. So maybe it is linear. And for space, we are actually, if you're going for the map way or well as for the other also, they are almost O of n, right? All of them. Even this one also, I'm using two arrays, right? For one for the frequency and template. So it is O of n.
The map or array has only 26 memory. I think it's a constant.
Yeah, because if you see the word length, it says is less than or equal to 50, and actually the pattern length on words single word is also less than 20. So yeah, maybe roughly same. Yeah. Oh yeah, you were saying it's, yeah, it has to be constant because all of them are the same almost. Yeah. Okay, shall I move to the second problem? Okay. So the second problem is a shortest path with alternating currents. So this is a very clear graph problem. What it says is we are given a graph of nodes n, and in this graph there are edges, and they are colored edges. And there are two type of colors. One is the red and other is blue. And so we will have either a red or a blue or both of them. So therefore there are parallel edges also, there are self edges also. And then we need to go start from 0th node and traverse to each and every node and find the shortest path of each and every node. So I start from 0. If I'm giving an area of length 3, then I start from 0. So 0 will always be 0. The shortest path to 0 with 0 will always be 0. And if I go to 1, and if I have a path existing from 0 to 1, so I will say it is 1. And if I go from 0 to 2, and if I have two paths, two edges connecting to node 2, so we are node 1, so it will be 2. So then I will just write 2. But I need to find the shortest path. So the only trick here is because we have two different color of edges. So if we don't find it, also one thing is when we are traversing, we need to have an alternate the colors. So if we start with the red edge for 0 to 1, and then we go for another from edge from 1 to 2, if it was earlier it was red, then we need to switch it to blue. Okay, so we need to find the path that way. So this is the only a tricky part of the solution problem. And when it says the shortest path, the things what come to my mind is I can't use a Dijkstra because it's not a weighted graph, right? And if I go for the other, whatever the Bellman-Ford, I think time complexity is slightly more. So I thought of using a simple BFS, traversing.
I have a question about the question. So let's say self edge, that means a node can point it to itself, right? It's like a loop there.
Yep.
And then it also say that parallel edges, that means I have two nodes, node 1 point to node 2 and node 2 point back to node 1, right?
Yeah, actually it's a directed graph. So parallel edges, what I infer from what they say is like we have two type of edges, right? One is the red edges and the other is the blue edges. So you can have a node edge starting from 1 to 2 in both of them. You can have it in the red edge also as well as on the blue edge. So that is what I actually get from what they mean by parallel edges. So
Okay.
you can have the same edge. Sorry, go ahead.
So in one direction, there could be two edges. That's what you say. Okay.
Yeah. Because if it's a reverse direction, then I would say it's not in my path. It might be for a different path, right? So that is what parallel edges I mean. So yeah, that also can be true. But for the problems, I'm trying to find the shortest path. I'll always try to look for a forward path. Yeah, in some cases, the backward path also might be more of a concern. But here, if there are parallel edges, I'm assuming I'm having a similar direction for both the colors. Okay. So the implementation is like a simple BFS traversal. And what I've done is, if you see the problem, the function entry function, it is given, there are two vectors for, one is for the red edge and other for the blue edge. And then is the number of nodes. So I create an adjacency list for the red and the blue. So if I actually, I'm using a map, a single map for a single edge, color edge, and I'm actually combining both of them in a single array, so I can traverse them very easily. So I'm using an array of two elements, and each element is pointing to a map. Okay, and I'm just actually including them in populating the adjacency list, and I'm using a queue. So I start with both the edges, blue as well as the red, and try to traverse it wherever I find a path. So when I'm traversing with the blue, I don't find it, then I go for the red, and wherever I find it, I take the minimum of the distance. So start with this queue over here. So this first one is a starting node, which is a zeroed node, and then this is, I'm identifying 0 for a blue color and 1 for 0 for a red color and 1 for a blue color. So I'm just pushing both these values in the queue first, and this I'm using a distance array to map the distances from 0th So this is the color again, 0 and 1. And then I'm starting from 0th edge. So sorry, 0th node. So, and the value will be the distance for this particular node. Okay, then again it travels in the while loop and keep popping each and every node, and I check for each and every adjacency list for a particular node, and then this distance I'm actually using for like checking if it's a earlier visited or not. So I set this distance to int max value, and whenever I get a value, I just store that value, and the int max disappears from here. So, and then if it is, I only enter here if the earlier value is not being is equal to int max, and then I push in the queue, and again I traverse the whole thing, and then at the end when I have all the distances, I just take the minimum of them and then return. So I am sure there might be different ways also of implementing it, but I thought this simple BFS traversal is easier as well as a good way of doing it. So that's the way I did.
Hi Santosh, can we go with the example and then actual?
Okay. Okay, so let me take a better example, right? So this one. Which one do you want? Do you have anything specific? So shall we take the fifth one?
Yes.
Okay. Okay. So here the node is 3, right? And then we have 2 edges for the red and 1 edge for blue. Okay. So if you point out here, okay, in this case, so this is the red edge, right? So in this red edge, what I'm trying to do here is, in this case, the x will be 0 for the, if I'm taking the first element here, right? And y will be 1, okay? And for the second one, it will be 0, and then it will be 2. So
Yes.
for the 0th node, actually, I'm having 2 paths. One is to 1 and the other is to 2. So these both are red paths, right?
Yes.
Right. And for the blue edge, I don't have any value for 0. It is from 1. Okay. So it is only for the node 1. It starts from node 1 to 0. 0th node. Sorry. Right.
Yeah.
So this is the way my adjacency list here. So when I go and enter for the red 0, 0, and 0, 1, okay. So the 0th node is already there. So my output array, suppose if my output array is like, so first I will make it something like -1, and -1. Okay. And then I've entered this value over here. Okay. So the distances are 0, because so I just make this distance as 0. Okay, this is what is initialized over here. Okay, either of it. And then when I enter this route, so I take the first red one, right? So the red actually, so the current value is 0 and the color is again 0, right? So when I come here in the adjacency list, okay, so the color is 0. So I need to go and take the red list. So red list, we have 2 points starting from 0. We have 2 edges going to 1 and 2, right? So in this we have 2 edges. So this will actually this v will be actually 1 first, and then the second will be 2 value, right? So then
Yes.
the distance value now, so we have a distance. So this is, I should actually have said it for the second one also here. Okay. So -1, now it will be 0, okay, and then -1 and -1, right? So this was for 0, which is red. Sorry, this is blue. And this is 0, red. Okay. So when I come here, so this is the distance array, right? And this one. Okay. Okay. So here, if I come, and then when I say 1 minus 0, it is actually going to the next one, right? So I look for this intermax. Okay, it's -1, but it's into, just assume this for as an intermax over here. And then I look for this value. So intermax value. Okay, so this will be distance of intermax is -1, and then I come here, this will go from 0 to 1, so it will come over here, and then I will add this 1 to this place, right? So it is the color, earlier value of color, which is the u, right? So u is 0 in this case, so this value of the red, okay, plus 1, I'll add it here in the first case, right? So for this first node, then I go and I again reiterate for this one, and I come for the second value, which is the second node, and I do the same thing over here because the color is 0 over here, and there is 1 minus 0 for, so I actually substitute this value as 1 over here, right? So, and I think when I go, this is the only, because I'm just pushing both of them again, okay? So I will push, so V will be 1. So my Q will be now, will have 1, and color will be 1. And the second will be 2, and the color will be 1. So when I come here again, and I try to pop both of them, okay? So I won't find any adjacencies for them, right?
Yeah.
Yeah, so then I exit this loop. So I'm having only this much array. Then I go and actually compare which are the minimum of all of them. So it is 0, 0, 1. So this will be int max, sorry, right? So that's not -1, int max. So if I compare which one is the smallest value, so it will be 0, 1, 1, right? So it will be
Yes.
0, 1, and 1. So that is done over here. I just take the minimum of it and then later. So if that is an intermax value, I need to make it 1. So the node is not reachable. So, but in this case, the node was reachable. So therefore, our answer matches with the output.
Yeah. Thanks.
Okay, thank you. So any questions, any more different approaches, anyone want to share? Okay. So I will stop sharing, and Emily, you can start with the third problem.
Okay. Yeah. Okay. Yeah. The third question is a maximum frequency stack. The question is asked us to implement the frequency stack, which simulates the operation of a stack-like data structure. As we all know, the stack is first in and last out. And this, the name is frequency stack. That means when we pop out, it's not pop the latest push element. It's pop out the most frequent element. As it showed, the frequency stack has two functions. One function is push, that's the same as the stack. But for the pop function, which removes and returns the most frequent element in the stack. If it's a tile for the most frequency element, we should pop out the latest push element and remove it from the stack. Yeah, I go through the example. Okay, wait for a moment. I'll share another screen. Yeah. This is example 1. It has several commands. The first is construct a frequent stack and push several elements into the stack and then pop them out. Yeah, let me go through the examples. First, we push 5 and the frequency is 1 now. And then we push 7. There is no 7 here, so the frequency is 1. And we push 5. There is 2 5 here, so the frequency is 2. And then is another 7. We have 2 7 now. And then we push the 4. We haven't 4 before, so the frequency of 4 is 1. Then we push 5 again. So we have 3 5 here. So after the push command, we have 3 5 2 7 and 1 4. Now we'll pop the stack. As I show, the max element, the max frequent element here is the frequency is 3 and the element is 5. So when we pop out the 5 and the frequency become 2. We can see from here, when we pop, we got the 5 now. Yeah, and then I'll pop again. This is the second pop. Now there is a tie here. The max frequency element is 2, but there the 5 and 7 also have the 2 frequency. Now we'll look at which one is the latest push element. And we track back and we can see the 7, because the 5 is already popped out, and the 7 is the latest push element. So we pop out the 7. And the frequency of 7 changed to 1. So we got the 7. And then we popped again. The maximum frequency is 2. And so I pop 5 here. And the frequency changed back to 1. And we got the pop out element is 5. And the last pop, the maximum frequency is 1. So we popped 5, 7, 5. So the 4 is the latest push element. So we pop out the 4 and the frequency changed to 0. And we got the 4 pop out element. Yeah, that's the process of the frequency stack. Yeah, work. Is it clear for this question?
Yeah, I think the problem statement is clear. So you are saying that we need to push as and when the elements come, and when you want to pop, we just have to look at the frequency first, right? And then we need to look at the order. Yeah. Okay.
Yeah. So
in the output, there are none. So when do we get the none?
this none, because the push command is the void function. So there is no output for the push command. So the output is none.
Okay.
Yeah. We can just leave it as it is. Yeah. Okay. Yeah. I go back to the question. And, okay. Yeah. So for this question, my first thought is to have a map to count each element's frequency, because when we pop, we have to find the maximum frequency. So for my data structure, first of all, I have this ordered map. It's a map to build the mapping. The key is the value, like the element we push into the stack 5, 7, 5, 7. The key is the value, and the value of the map is a frequency. Each time I push some element into the stack, I just increase the value, the element I pushed into, increase the frequency of that value. Like when we pushed 5, so the M5 is plus by 1. And this map is to count the frequency of each element. And another thing is when we have the several elements has the same value as I showed before, like the 5 has 3, the 7 has 2 frequency. In that situation, I have to figure out what element had that frequency. Let me see if the 5 and the 7 also has the 2 frequency. I have to figure out the 2 frequency has the 5, 7 element. Yeah, this is another map here. It's a frequency map. It's a map of the frequency to the vector array of the value 1, value 2 here. Yeah, and another thing is each time I have to keep track of the max frequency. It helped me to find the max frequency when I need to pop out. Yeah.
So Emily, in that vector,
Mhm.
on line 31, you also maintain the order of the value, right?
Yes, yes, yeah, yeah. Because from the question, one is there is a type for the most frequency element. I have to pop out the latest coming push element. So each time I append push the new value at the end of the vector, like
Oh.
like this. I first push the 5, and then I push the 7 here. Yeah. So 1, 5, and 7 had the same frequency, maximum frequency. I could pop out the 7 because 7 is latest push element.
Okay. So the last one is always the latest one, what you have pushed in the
Yes.
vector.
Yeah.
So,
Of course, you can change your order each time you can insert the new element in the beginning. That's the thing. It depends on what order you push the new element into that array.
so one question, I know this is perfect implementation here for this at least the data structures. So you have used map instead of using an unordered map for the frequency to vector mapping, right? So you could have used an unordered map also, right? Because the map is again a log of n.
Yes, but for the frequency, I have to use a mapping step on ordered map because I need the maximum frequency. Yes, yeah. For example,
Sorry, go ahead.
yeah.
You can keep max frequency. You can get it from the map, right? Because the map is the order already. That imply the order already.
Yeah, that's the situation I also think about. But in this situation, like the most element is 1, is like
3.
3. That means if the maximum frequency is not continuous, like this is a 3, and I have the 7, 1. Oh yeah, it has to be continuous. Yes, it's decreased to 2 and 1. Yeah. I think so. Yeah, I can use this as
Yeah, it's okay. Just
yeah. I just think if the max frequency is changed, I have to have the second maximum frequency.
Yep. That makes sense too. Yeah.
Yeah, but I think it could be an ordered map. Yeah.
And it seemed to me that the way you implement on line 31, the value in the vectors are always distinct, right? There should not be duplicate value in that vector.
You mean the vector?
Yeah. I mean the value, like for example, we have 5 and 7 right now, right? We would not have the case of like 5, 5, and 7. There's no duplicate in that vector.
It can have the yes.
Yeah, I think what he's saying, you can have duplicates, but you are not storing duplicates because for each and every frequency, you are storing the different values there, right?
Yeah.
Yeah, but if the frequency got reduced, in that case, we have to shift from one atom to another atom in the map, right? If its frequency got reduced from 3 to 2, then 5 will not be in the same vector, right?
Yeah. We have to change the, like if the 5 frequency from 3 to 2, the previous one I have the map F2, F3 had the 5 Yeah, but now the 5 frequency is changed from 3 to 2. I have to change that to F2 have the 5 element.
Well, I would say like whenever you are entering any value, you are always going to enter from the first frequency, like F1 5, F2 5, and F3 5 for all the 3. And then when you are actually popping it, you will just pop the F3 5 first. So your F2 and F1 5 will still be there. So when you come for
Yes.
this F2 5, so you don't have to do anything. It is already there, right? When you're mapping it.
Yeah. Yeah. When we pop, we just need to deal with the max frequency element. Yeah, like the move. If the 3 is the maximum frequency, when we pop 1 5 from here and change the frequency from 3 to 2, and change the 5 element from the F3 to the F2. Yeah, that's the only thing I need to do when we pop out. Yeah. Is it clear?
Yep.
Yeah. So yeah.
So we need still 2 maps, right?
Yeah. Yeah, you are correct. We need 2 maps. One map is to record each element frequency, and another map is to keep track of the frequency, different frequency with its value. Yeah, element values.
Because the frequency is in the order, so the second map can be replaced by an array.
So when frequency change for an item, so you remove that item from the vector and move to the another frequency item?
Yeah. Yeah, I'll go through the increment, yeah, to explain how to do the pop. Is that okay?
Yeah.
Yeah. Yeah, for the push, it's quite straightforward. Yeah, each time we push an X, we have the frequency end by 1. And for that frequency, we push the X to the vector. Yeah, push back X to that frequency. If the frequency is bigger than maximum frequency, we update the maximum frequency to be the biggest frequency. Yeah.
So just to make it clear, so whenever you are pushing the same element, so always next time you push, suppose if you push 5 first, so you first increment the mx frequency, right? So it becomes from 0 to 1, and then you push 5 in the first frequency mapping vector, right?
Yes, and the 5.
Yeah, and when you go for the second, you actually increment the frequency again for the second 5.
Yeah.
And then in that you actually, when you have incremented the frequency, so you map the second 5 with the second frequency, right?
Yeah.
So it's like you have 2 entries for the 2 5s of in the F.
First is 2, and that frequency is 1. And for the second second 5, the frequency is 2.
Yeah.
Yeah, and the maximum frequency initialized to be 0. When we put 5, the first 5, the max frequency began to 1. And when we push the second 5, the maximum frequency increased to 2. Yeah. This is always keep track of the maximum frequency, no matter the frequency is come from 5 or come from 7. It's just to keep track of the biggest frequency. Yeah. This data set. Yeah.
Right. So in your F data structure, So you will have both these entries, 5, 1 and 5, 2,
Yes.
right? Yeah.
Yeah.
1, 5 and 2, 5, right?
Yeah. F1 push back. Yeah.
So it will have 1 and F2 will have another. So it will have
Yes.
5, sorry, yeah.
Oh, yeah. Maybe I should. Yeah,
No, that's correct, yeah. So
remove
F2 you'll have 5, F1
Yes.
you'll have 5 and F2 5, yeah.
This one, F2 have the 5. Maybe I need to remove the F1.
No, you don't have to remove actually. It is because it gets popped out and then you again come back to the F1 on its own.
Yes.
You don't have to do anything. Yeah.
Okay. Let me go through the pop function. For the pop, the things I need to do is to return the maximum frequency element. That element is F maximum frequency back. That means that's the last element I put it into the F max frequency. So I have a temp variable to get that value, and then I need to pop it out. That means I remove it from the stack. And if the pop out element frequency is equal to 0, for example, if the F1 is 5 and the 1 is maximum frequency now, and I popped out the 5, so the 5 has the 5 previous has 1 frequency, but when I popped out 5, the frequency become to 0. That means in the map, I have no 5 now, so I have to erase the 5 in the M map, in the in this map. This is the things I do, and the next thing is to update the F frequency size. If the F1 has only one element, 5, when I popped out 5, there is no element in F1. In this situation, I erase the max, I'll erase the F1. Yeah. If the F size is not 0, I keep track of the maxi frequency to the previous one. That means if the F2 element, like I have the only element 5 here, when I pop out 5, pop out 1, 5, there is a need to be a 1 here. So I think maybe it's not necessary for this one. Yeah.
But yeah, you might have to decrease the max frequency in some cases. So I think that might be required though. But yeah, but you can check, yeah.
Yeah.
So, yeah, what the R begin does, the function?
Oh, R begin, that means the there is a F1, F2 here. If the R begin is the end of the F map, that means that is the largest F here.
Okay.
Yeah.
So it's the last
Like
point of the array.
Yeah.
Yeah, end of the array.
Yeah. Yeah, that's the reason why I use a map instead of the unordered map. I just think I need to keep track of the maximum frequency in the F map. So yeah, I keep the max value. If it's 0, the max frequency it reset to 0. Maybe someone has another approach. Yeah.
Yeah, I think this is good, but I was thinking instead of using a vector, you could have used a stack also, right? So that is what they talk about that in the solution.
This one we use a
Right.
stack.
Yeah. You can use just a stack.
Yeah.
Yeah.
Because, yeah.
Though I've not tried, but I'm just looking the problem here, and I'm thinking to use the stack and the priority queue and a map.
Yeah, I think the priority queue is also a good option. Yeah.
Priority queue.
Yeah, so how I'm thinking here that the stack we will use to push the item to the stack. And then I'm thinking to have a map with the item. The key will be the item itself, and there will be a pair. That the pair will have the count and the position in the stack, and then push that pair to into the priority queue.
With the priority queue, how you keep track of the order?
Yeah.
You have to somehow keep track of the order based on the time or something.
Yeah, that's why I'm saying that in the priority queue, I will not put the count only. I will put the pair, and that pair will be actually the count and the index in the stack.
Do you mean you keep the priority queue compared by the frequency of the element, not by the element value? Yeah, because
frequency plus the index.
Index.
Index in into the stack.
So I think what the way he is saying is the index is the way you are entering here in the vector. So you have those indexes, right? They are the inherent indexes for the vector, what you are entering here. So that is what he is trying to say, I think.
Yeah, if you have
that's just a thought. I mean, I have not tried to implement it. just brainstorming.
Yeah.
No, that's good. One way of doing it too.
Yeah. Okay. Yeah. When I implement this question, I have some inspiration from the LFU. There is a LeetCode question, LFU. In that question, also need to keep track of the maximum frequency. Yeah. So yeah, it's it use two map. Yeah, and iterator. Yeah.
So LFU means cache type, least frequency.
Yes.
Okay.
Yeah, that's the least frequency. Well,
I think least frequently used.
Yeah. Least. Yes. Yeah. Least frequency used. Yeah. And there is another cache. It's
LRU.
Yeah. The least recently used. Yeah. Yeah, I think this three question has a lot of common point.
So one of the another approach for this means just coming in the mind, use a map, and in the map the key will be the element and the value will be the node, and the node itself has a previous and next pointer. So means not exactly for this one, but the other type of cache.
Yeah.
So doubly linked list as a node, and that will be the value of the map. So we can move anywhere that node in the, and we can maintain the pointer.
So you are saying you will just have single data structure?
Yeah, means yes, the map key will be the key value, value of the element, and the value means the value will be the type of node.
Okay.
And in the node we will keep the frequency means value and frequency and the previous and next pointer. So as the frequency got changed, right, we have to change the pointer, and that will work as a doubly linked list. That node means previous and next pointer, so it can move anywhere in the map.
I think the C++ has a DQ, so we can use that too, right? Yeah.
Yeah, could you like to show us how to implement this data structure? Or, yeah, I can stop the share and you can, maybe you can share your screen.
Well, I think she was just brainstorming, right? Yeah.
I never shared the screen before, but so we have 5 and frequency is 1, right? So as usual, I don't know, but the idea was like 5 will be the value, key value, right? And there will be the node which is containing previous, next, and key value. So previous, next, and 5 and frequency. So this will be the pointer, pre-pointer P, and this will be the next pointer. And when we will add, means as we know, the once again the 5 came, right? So frequency got increased too, right? So, and sorry, in our case we have to give another one, 7. And this previous and next pointer, where to point, we decide on their value got changed, right? Suppose it is 2. So previous, actually whatever the max frequency we have to keep on the header. Suppose 5 has a 3 frequency. So this will be my head. Are you able to hear me? Hello?
Yes, yes.
Yes.
Oh, no, I'm doing this first time. So representing head, and this will be my tail. Right, and then I will decide where I want to point the next. Right, both ways, previous and next. There will be both ways. So so this is one data structure, which is map, right? And the node will be, I can adjust my node whenever the new atom get pop or get push. Then I have to also means I will write the function move to the top, means who will be the top on this, which is the maximum frequency. I will move that to the head and maintain these pointers. So if you know doubly linked list, right, the same thing will work here, like maintaining the pointers. You have to just change the pointers.
So we'll have 4 cells in a node, right? One
Pardon,
would be
please?
previous. We'll have 4 cells in a node, one for previous, the other for next, and other one will contain the key value, and other the
Yes.
frequency.
Yes.
Yeah.
So node content itself as a key value, means number and frequency, and this one is the hash map, like, and this is the main key of the hash. When the atom get come, right, like in if we are adding the atom, we will look for this value, and then we will adjust the node according to that.
I think
We'll
the
check
prev
the
and
frequency.
end, the prev and end will the pointers of the data structure, right?
Node previous and next will be the part of the node.
Okay.
Yeah,
Okay,
it's a map, and first I push what if we push 7? Yeah, push 7 here, and we need another map with the key of 7.
So you want to say like new atom, like if I
Yeah.
new how to get atom add?
Yes, yeah.
So if atom get 4 add, then it will have as a less frequency, right? It tail will get modified. That time I have to update the tail and update the pointer of next. Next will be pointing next here. Next. Okay. So there is, if actually I have to meeting at 10, but I can just briefly tell like how this pointer will work. Whenever we add, right? So I know okay, one thing I'm missing here, one thing I got to know, like order, right? The order, if I have a same frequency.
Exactly.
Yeah.
That deadlock
So
situation will come.
yeah, so while updating the pointer, I have to keep in mind, like I have to keep the order
no,
as well.
actually, when you are using this list or whatever the structure in a map, right? So each map's index will be having pointing to a frequency, and I think you need to have that, use that index for that frequency and just put in those nodes there. So if it's the first element coming for the first time, then you need to look for the first index and then put that element there. And then you come for the second time of this for the same element, then you need to go for the second index and put this element there.
So
you,
you
if
want to
you're
say
having,
like instead of 5, I have to keep the frequency here?
yeah, that is what I was thinking. That is what I thought it was.
Oh, okay.
So are you saying like you are having a 5, you are mapping that 5 with all the list of 5s?
Yeah, I was thinking like that. Like
Okay.
it is
But
depend
you
on the
added the
element.
4 here, right, at the end of the tail. So therefore that I got confused. So you added the 4 to the 5 list, right, here. So therefore I thought it is a single.
No. So yeah. So here we don't have to, we can maintain the order with the previous and next pointer whenever the anything get added, right? We have to modify all, means like whatever the pointers needed.
Okay. Maybe, yeah. It's worth thinking. Yeah, that's good.
Anything?
Okay. Yeah, any more questions? So we just stop the recording.
I have to stop the screen, right?
Yeah, you can just stop the screen. Yeah, no problem.
Just close the screen, we'll stop the screen, right?
Yeah.
Okay.
Okay. I'll just